Okay, I think we're online.
I
We're in Delaware.
was doing,
Delaware?
I was doing, yeah. Perfect.
A sphincter says what?
I watched that recently. It's still a really good movie.
It's still pretty funny, right? Like I think it was ahead of its time.
Yeah, it was. I think I lamented to you when it happened, but seeing them do a DoorDash commercial after watching that, I was just like, the whole point was that these characters weren't about selling out.
Oh,
and
yeah.
they're like selling out of the Super Bowl commercial. It was like capitalism destroys all irony.
I remember that. Yes. It was bad. I felt a little bit heartbroken because I don't think Mike Myers or Dana Carvey need the money, right? But maybe they thought it was going to be funny. It's like, wouldn't it be funny?
Maybe. I mean, it would be funnier if they made a third movie and they were the same characters, but like actually 60 years old. That would be very funny. I would love that.
All right. Well, at any rate, we are on Twitch now. We're doing day 12 of Advent of Code in Rust. Why don't we just dive right into it? We can go back to Wayne's World in a sec.
We'll get there.
Dom, you're a little bit ahead of me, but I'm going to go ahead and read the problem prompt. Passage passing. With your subterranean systems subsisting suboptimally. Nice. The only way you're getting out of this cave anytime soon is by finding a path yourself. Not just a path. The only way to know if you found the best path is to find all of them. Fortunately, the sensors are still mostly working, so you build a rough map of the remaining caves, your puzzle input. For example, start A, start B, A, C, A, B, so on and so forth. This is a list of how all the caves are connected. You start in the cave named Start, and your destination is the cave named End. An entry like BD means that the cave B is connected to cave D. That is, you can move between them. So the above cave system looks roughly like this little diagram. I don't know why there's capital letters and lowercase letters. Maybe that will become clear in a second. Your goal is to find the number of distinct paths that start at start, end at end, and don't visit small caves more than once. So this is like we're trying to do basically like a traveling salesman problem here, right? We're trying to visit everything. There are two types of caves: big caves written in uppercase like A, and small caves written in lowercase b. It would be a waste of time to visit any small cave more than once, but the big caves are large enough that it might be worth visiting them multiple times. So all paths you find should visit small caves at most once and can visit big caves any number of times. Given these rules, there are 10 paths through this example cave system, and they've got all the examples. Note that in this cave system, cave D is never visited by any path. To do so, cave B would need to be visited twice, once on the way to cave D and the second time when returning from cave D. And since cave B is small, this is not allowed. Here's a slightly larger example. Okay. So I'm guessing there's lots of caves because they're using double letters here. There are 19 paths. Finally, this is an even larger example that has 226 paths through it. How many paths through this cave system are there that visit small caves at most once? And here's our puzzle input. Okay, not too bad.
That's big enough.
Okay.
Cool.
I'm going to copy this down and we are going to get cracking.
Love it.
Let's talk maybe abstractly about the problem a little bit. We build a graph, right? And in this case, graphs, I think, have two main representations. One is an adjacency list, which essentially is this, right? And then the other is a list of, so adjacency list is also a list of edges, right? And then the other is a list of nodes where each node has a list of its neighbors, right? Those are like our two main ways of representing graphs, I think.
Yeah. Wait,
I guess there's lots of variations.
The small, yeah, I was gonna say the small big constraint actually, I think, makes this problem somewhat easier to do in a naive sense, maybe.
Yeah.
Because I feel like a lot of paths eliminate themselves very quickly. Are there any big big nodes connected to big nodes? No.
It doesn't look like it.
So that also means there's no like infinite loop path through this, which is also helpful.
Yeah. So yeah, like we can either do this as a breadth first search or a depth first search, where essentially we start at start, and then all of the neighbors of start, we create a new partial path from start to those neighbors, right? And we stick those paths onto some kind of queue or stack, some kind of list that we're going to process. And then we go through each one of those. And so on and so forth, right? Up until the point that we also need to keep it. We also, each path, when we visit it, we need to know the full length of the path, so we're aware of which lowercase caves we've already visited, so we don't try to explore another one that we don't try to go backwards at least once to to any cave that we've already visited on this path. Whether we're doing breadth first search or we're doing depth first search, we run the risk of duplicating our work, right? Like we may go across something that we've done before, and in those cases, I think we need to keep some kind of set of partial paths that we have already stuck into the queue, right, and have already attempted. Otherwise, we're going to just
if we go breadth first, is that possible for this graph? Because with no big to big nodes, there is no way for us to loop back to our starting point. Like we can't. There's no way for a path in this to loop back to start, or like if you insert paths that are start to all of start's neighbors, and then from there iterate over that and insert past all those neighbors, like I think breadth first actually doesn't duplicate work, because actually returning to a node is a new path. So like if you can go to a small and then back to a big, we shouldn't consider that duplication. That was like a separate path in their example.
I'm trying to think if there's is there a way that we can actually get a duplicate path? So so you say breadth first will guarantee a unique path. What about depth first? Is there a difference?
That one I can't reason about as clearly, but I bet it has a similar constraint. I think just the way they gave us the data, we don't have to do a lot of duplication.
Is it the fact that you just can't double back at all prevents duplicates?
Except across some nodes, but that double back is like that's considered a feature, not a bug for this one. Like they want to see that double back as a path. Yeah.
I think
that helps.
Whether it's depth first or breadth first, we can't create duplicate paths, right?
Yeah.
Okay.
I guess I was having trouble reasoning how you would keep track of. I can't picture that recursively.
Sure.
Depth first. That's my struggle right now. But yeah.
Okay, so maybe the thing to do here is, I like the idea of an adjacency list as the first way to represent this graph. Well, no, if we're doing this like tree style, we kind of want a list of nodes and all of its neighbors, right? So what's our data structure?
Like a hash map?
Yep, hash map. And the key is the node that you're on, and then like there's a vector of nodes that are your neighbors. It's like a neighbor list. Yeah. Okay, so it is a neighbor list then. Okay. Let's do it. So it's going to be yeah.
I was just curious if start. I'm glad start is spelled lowercase, because you can't double back to that at all, which is probably also important.
Yes. And this is a vector of other strings. Does that seem about right to you?
Yep. And the lines are, oh, they're all pairs. Cool. 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 Cool.
I'm going to split the lines on a hyphen, right?
Mm-hmm. Yep.
And then the first node is, I'm just going to call it A equals chunks.next.unwrap. Let B equals chunks.next.unwrap. And then we are going to, so Rust has a really cool API for interacting with hash maps. And the way it works is that we get an entry based on the key. Entry using key A. And I think we want to convert these to strings.
Oh, are they not implicitly when unwrapped?
They are, you get an option from next. And I think
what is it unwrapped to?
It unwraps to just a string of, it unwraps to an ampersand string. And
oh, okay. Yeah.
So I'm a little bit foggy on the differences between these, but this is essentially like a slice of characters, UTF-8 characters, or a slice of runes. This is like an additional wrapper that has like a bunch of extra functions on it, and the guarantee that the buffer of characters is on the heap, so that if you pass that string around and mutate it, you'll still be pointing, like everything that's pointing at the same string will still have the same buff, like the same characters that it's pointing at.
That's great. Okay. Yeah. Cool.
So that's what toString is doing. toString, this has a corresponding function called asStir, which basically gives you the reference to the underlying buffer, right? Technically, I could make these ampersand stir there.
Yeah. It doesn't seem super valuable though for the actual nice operations we get on a string class.
Yeah. We'll see whether or not whether it matters or not, and I'll continue. I should probably just actually read again like what the differences are. In practice, what ends up happening is that I end up like if you have ampersand stir that you've gotten from a hash1 container and you want to use that ampersand stir in another container that you're mutating, it starts to complain that you've borrowed like not like immutable data. And then I'm just like, you know what, fuck it. Like, I just want to treat the string like a value. I'm just going to copy it and use that as the key. You know, that's basically what ends up happening a lot of the times. Okay. Gotcha. So the entry exists or it doesn't. But I think we can do or insert
or default. Oh, cool.
Yeah, entry dot or insert. There's actually a few things we can do here. Entry.
A little different than or default, yeah. Or insert with. Funny.
What is or default just returns a value. We can insert a value here. The question is, I think it's and modify or insert is what we want to do. So this is if something already exists. And what we want to do is we want to do entry dot push B. Or insert
a new
it's
vector.
just like a new vector, right?
With B in it, right? Or does it and modify apply to this?
Yeah.
Oh, okay. Yeah.
It's like this.
Neat.
But it's complaining a little bit. Variable move to use in closure. So we can do b.clone here. Again, this is like, okay. We're just making copies of it, right? Yeah.
sorry, why does the unmodify one need to be a copy and the or insert not?
Oh, it's just that one of them needs to be a copy. This one, basically, once you pass it in, when you push a memory value, because it's a string, you're essentially moving the string into the list. And because we moved it in this closure, it's just going to assume that, like, by just calling this and modify, it's a possible move. And so since it's moved, you've basically destroyed the local variable.
I see.
B. Yeah, essentially after this expression, the local variable B is no longer in scope.
So is it true that after line 16, the local variable B is also not in scope, but it's fine because it's not used together?
That's correct. Yeah, because we moved it. This sort of vector macro is essentially creating a new vector and then pushing B on top of it. You can think of it as doing that. Yeah,
that's really interesting. And I guess I've never seen a hash map interface like this, but I like it. But it's really interesting that it doesn't know that those are sort of exclusive operations.
Oh,
you can't modify or insert.
It's like the compiler doesn't know. It's not so much that this class doesn't know. Like the class doesn't know about what this closure is doing. And since this closure is doing moving, the compiler says, I don't know if you're going to call this closure or not, but I'm going to assume you are. So I'm going to treat that possible move as an actual move. And so you don't get to use B anymore. That's essentially what they're saying here. Now, you can avoid doing this by passing references. So if this was ampersand string, since ampersand string is a reference, you can pass it in there. And with references, you don't need to move any memory. They're just pointers to things. And then it would be fine in that case.
Okay.
So I'm going to just go ahead and print out what we've got so far in neighbors of.
I remember we only get 2 runs of this program. Let's see.
Cool. HR, VK, ST. So HR goes to VK. HR goes to ST. So I think the one thing we're missing is we want to go the other direction, right?
Oh, right. This does, because ST does need to include HR. Yep.
So in fact, this probably just needs to be a.clone up here. This is going to be a little bit awkward. All of these are like different chunks of memory. And then this is going to be B. And this is going to be A.
And it's A at the bottom.
That's A. Okay, so RT, you can go to start. Is that right? RT to start. And then start, you can go to RT.
Right? RT, yeah.
And there should be no dupes, right? Like the only way that we would ever have dupes is if like either
they gave us one.
Two of the same thing basically exist in the list or the reverse of it exists in the list, right? Okay, nice. All right, so we've got ourselves a nice little list here. So now we're going to basically traverse our paths, right? And a path is a vector of strings. Does that sound right?
Okay. Yes.
You wanted to do a breadth first search, right?
I think it'll be easier to reason about. By the way, is there like an ordered set in Rust? Because that's maybe. Oh, it's not a set. No, it's a vector. It's a vector of strings because we can have duplicates. Never mind.
There might be an ordered
set. I mean,
oh, somebody has like a custom thing that they made, but these are the only sets that you get.
Well, not what we want, so. Okay.
I think that our paths aren't going to be so long that I think even just doing like an iteration over them to like it's basically at most like 20 items in it. So maybe like that's like a set would help if it was like hundreds, right, or thousands. The first thing we're pushing back is a vector that just has start, right? And start is not a string. So start a string literal like this is an ampersand str. So we have to do string from to get that.
Q.
Oh,
Okay.
Q needs to be mutable. And then we're going to do while Q is not empty. Right?
Yep. And then
there might be a way to do like
oh, I like that pattern. Yeah, if it lets us.
I forget because you can definitely do this with if. Like you can do like if let okay foo equals bar, which where bar option, and then you can refer to foo in here. I'm pretty sure that's possible. So I feel like technically this should be able to work. Sum, it's not okay. Okay is what for results, sum is for options. Like there's like an enum that has some value and none as the pair for option. And result is okay, some value, or error, some error. That's the dichotomy or the whatever. Okay, so now we have a path. And we want to get the last node of the path, right? So let last equals path.last.unwrap. And then we want to get the neighbors, right? Oh. Cannot move out of index.
Is last is a ampersand capital string. Does that matter?
What if we do dot get?
Cool.
And I think we can unwrap this. I think it's fair to say that like everything's going to be in there, right?
It'd be weird if it wasn't. Yeah.
Yeah. Okay, so now we've got a list of the neighbors, and what we really want to do is actually iterate over these, right? And what we're going to do from here with the neighbor is we're going to continue if the neighbor is if the neighbor is lowercase and it's already in our path, then we want to skip this neighbor, right?
We skip it, and everything else gets added, which is small nodes not in our path and any large node we see. Yeah.
Right. So if n dot, how do I get the first character? Is it just this? Okay.
What can we check here? Can we check that like two lowercase is the same as the original or something?
We can check the first character and just say, I think we can just say,
oh, is.
I hope I'm still streaming. Looks like I lost side code.
Oh no. I'll check fetch real quick.
Yeah.
Yeah, we're still streaming.
Okay, cool. I think I'm back. Hello? Okay, yeah, we're back.
Yeah.
Sweet. All right, so how do I get a particular character out of a string? I'm just trying to check to see if the string is lowercase or not, right? We could create a set up here of the lowercase and uppercase ones just so we don't have to do this every single time, but it seems weird, right? We could do n.chars.first or .next .unwrap. That's the first character is ASCII lowercase. That's really ugly, but that's what it is, right?
That's convenient. Yeah.
And that chars next unwrap is ASCII lowercase and path dot contains n.
Mm-hmm.
Continue. Right. Go to the next one.
Yeah. Contains is going to do. Does it have a sense of like a normal, like an inequality?
It will use partial equality.
Partial equality. Okay. Yeah. That's trying to get my words around. Perfect. Yeah.
Yeah, it's not going to do like a are you the same physical thing in memory? It's going to compare the content wise comparison of strings.
Yeah, I think I was wondering if there was a comparable sort of interface that classes implement and defaults to.
There's
like
the partial equal
assignment.
trait. There's a partial equal trait, and then there's also the equal trait, which is different than partial equal. Yeah. And those are just functions that you have to implement on a particular type, and then it says, okay, you satisfy the trait.
Mm-hmm.
Traits are more or less interface. You can think of them as interfaces.
That makes sense.
Okay.
Yeah.
So what are we actually doing in this loop? We're like going to create a new path, right?
Yeah, we have to. We have to duplicate the current path and push it with n. And stick it back in the queue. And I guess the missing check here is, yeah.
If n is equal to end, then we've found a new path, right?
We found a path, we don't push, and we count. Yep.
I don't think Rust has a plus plus, does it?
Nope.
Which is fine. Plus plus is a little bit weird.
It would be 2 C++ of it.
Yeah. New path push n. And I think we have to clone this. And the new path needs to be mutable. And then we need to push this onto the end of the queue, right?
Yeah, queue that push back. Yep.
Okay. It's complaining about one thing.
That's the algorithm. Okay.
Oh yeah, we don't ever do anything with numpads, so we can just
print
it, right?
Yep.
Does that seem about right to you?
I'm pretty sure that's the algorithm, yeah.
Okay.
Let's see what we got. All right, this is gonna be bug-free stream number 2.
3,463. It did an infinite loop, which is always the good thing, right?
It's a good start. That is many.
Well, we got
Jesus. Okay.
Okay. Don't question it, Tom.
Well, it's just like every Rustation I know who is really really championing the world of like bright bug-free code. It's true. It's fucking bizarre.
Yeah, I mean, honestly, this year I've had not such a great track record of doing it right the first time. I think partly I'm just trying to remember how to do Rust, but In Rust, you can still be off by 1. You can still definitely be off by 1.
Yeah, that's fair. That's fair.
Yeah.
There's some very pleasant guardrails on here that are, the whole process is kind of annoying, but the guardrails are really working for you.
Yeah, all that borrow stuff that we're talking about, how like I have to clone things. What it's really actually preventing me from doing is referring to the same complex data structure with 2 different variables. Because I could modify it. Sometimes you want that, but probably most of the time you don't. And what you can have happen, I guess that problem is just called aliasing, right? You can have spooky action at distance where you use one variable to modify something. And then unbeknownst to you, you're using a different variable name that refers to the same chunk in memory. And suddenly you're getting weird stuff. And Rust prevents that completely, even when you want it to have happen, you know?
Yeah, different problem, but yes.
Yeah, yeah, for sure. Okay, so
done.
Yeah, all right. So let's just go ahead and make a copy of that to 12b.
Mm-hmm. Oh, and time to reload your VS Code window.
Yeah.
Yeah.
So it was a few keystrokes incantation to get going on the next problem.
Man, I don't know how anyone programs anything, to be honest. There's a lot of magic words.
It's a lot of fuss. Lots of muss, lots of fuss. Part 2. After reviewing the available paths, you realize you might have time to visit a single small cave twice. Specifically, big caves can be visited any number of times, and a single small cave can be visited at most twice, and the remaining small caves can be visited at most once. However, the caves named start and end can only be visited exactly once each. Once you leave the start cave, you may not return to it. And once you reach the end cave, the path must end immediately. Now, the 36 possible paths of the first example are blah, 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 blah. The slightly larger example above now has 103 paths through it, and the even larger one has 3,509 paths. So they're saying you can do one doubling back of the lowercase.
That's correct.
Okay. So maybe this check says
we need some sort of like,
if you're lowercase, go through and count the number of unique, or make like a hash map of lowercase, or give me the like the most number of times a single lowercase cave appears in the path up to this point, and if they're all 1, or if it's less than 2, the max is less than 2, then you can push this one on at the end, and that'll be your double, right?
Yeah, filter all uppercase, map count over all lowercase. And if you don't have anything greater than 1, you're good. Yep. And special case start and end in there, or at least start.
So you're saying path filter, path.iter.filter. This is like a cave. And it has to be lowercase and it can't be start and end, right? So we're saying C is lowercase, and C, maybe it's actually even easier to say like C does not equal start and C does not equal end. And this?
So I think actually we need to, well, maybe keep going. I think filtering out start is maybe less important. We just need a special case sort of outside. Besides doing duplicate checking, we just need to make sure we don't go back to start. So like you can't, it's basically like if C is start continue every time. Or N in this case, yeah. Right. Oh yeah. Yep. And you'll get to end, and we already end the path at that point, so we don't care. Yep.
Okay, so we're filtering all the uppercase ones. And then what are we doing? We need to like actually count each one of them, right?
Yeah.
So we can reduce that into a hash map.
Yes, we have to. I'm trying to come up with a different data structure. Oh man, what is going on here a little bit? Give me 1 second. I'm gonna go pull my sweet potatoes out of the oven.
Oh yes,
BRB.
please do. How do you have your sweet potatoes?
I'm doing them. I have a nice big toaster oven, so I'm doing them in a toaster oven at 425 for about an hour.
Mhm.
I don't actually coat them or anything because you get a really crispy skin if you just sort of roast them dry.
Yeah, and then you just cut them open and go for it.
Cut them
Butter.
open. I'm gonna cut them open. I'm gonna do some beans and some red onions and some cheese.
Oh, okay,
Like
nice.
kind of
Savory.
a southwesty, yeah.
Bunny and I had sweet potatoes done that way, and we did butter and maple syrup. Actually, it was really good.
Well, that's good. A little sweet on
Yeah.
top of all that is fucking delicious.
Yes.
And it's perfect sweet potato weather out here.
Right.
And I guess will be for the rest of winter.
I don't love using full to do a hash map here. It's just, why am I not just using a for loop, right? It's one of those situations.
If I have a question, is it worth changing our path structure to just sort of be passing this all the way down? Like, do you want to make a tiny struct and like have the path and the map of the frequency map in there? Is that over engineering?
No, it's not. I think that's totally fine. Does the path doesn't even need to have the uppercase caves. Oh, it does because we need to get the last one, don't we? The path really just needs to know the last one, and then it's like the one you're currently on in the frequency map, right? That's what the path is. Is that right?
Oh God, you're right. Yeah, we don't need any of the previous nodes, do we?
Yeah. And it's the frequency map of just the lowercase nodes. Is that right?
Mm-hmm. I think that is right.
Okay. Well, shoot, let's do it.
Mm-hmm.
So this annotation, I believe, is actually I think hash open square bracket is an annotation in Rust. But then if the compiler notices that you're doing a function style invocation inside of there, what it's doing is it's expanding a macro. And so the standard library has a bunch of macros that know how to derive a debug function. You know, there's a debug interface, and it knows how to just say like, okay, recursively call debug on all of the primitive objects inside of it.
And same for clone. That's really handy.
For clone, yeah. The way that this works is that Rust has two different macro implementations. One macro implementation looks like a really buff version of the C preprocessor, where it's like a template language. Only that one's a little bit less foot gunny than the C preprocessor, and has like it's very unambiguous when you're talking about a macro variable as opposed to like an actual string of code. It also has, I think, type safety in the macro as well, which is cool. The other macro system in Rust, actually, basically, it's a little Rust program where your input is some Rust AST nodes, and then you emit another Rust AST tree. And I think that's how this derive is actually implemented. You can imagine just like writing a little program that says, okay, you're giving me like the structure as a kind of like a metadata structure of like what properties the structure have, and so I want you to like just basically write a new AST that like iterates over the properties and then recursively calls the debug print function for each one of those properties. And the same thing for clone, right?
That's really cool.
Yeah. And then I think we can do, just to make it easier on ourselves, I think we can do impl path fn new, and it just returns a path. I guess we need a current here.
Mm-hmm.
Something like that. Current just means that the property current equals the variable called current, right? Just like JavaScript.
Yeah. I was gonna say, can new just always start with start? How often are we calling new, or is that going to be a clone thing? Clone won't call new. Clone's going to do like a memory copy, right?
We should be creating a new path anytime we add a new path node onto something, right?
Oh, I'm sorry. It is a new path. Yep. Never mind.
But you're right. We're going to be cloning most of the time. You're absolutely right. We're going to be cloning most of the time. So maybe we are only doing this the very first time, right?
Yeah, I was going to say, I think this code only gets run once.
Okay. So what we're pushing, this is really now a vector of paths in the queue, right? Or rather, a queue of paths.
Mm-hmm.
And this now just becomes or rather string from this.
That's a weird one. Yeah. Yep.
Okay. So some path queue pop front. Last is no longer necessary. What we're just getting is path.current.
Mm-hmm.
I think we just have to borrow here. When you call get into a hash map, it doesn't need the actual value of the key. It just needs a reference to the key, because it's not actually needing to borrow that memory or anything like that. It just needs to do a comparison, right? It needs to hash it, and it needs to do a partial equal. Yeah. So it's just borrowing. Okay. If n is start, we're going to skip it. If n is end, we found a new path, and then we continue. Otherwise, we need to do our logic down here, which is basically to say, is it lowercase?
Is n lowercase? Yeah.
And this will lead to a continue, right? This is basically like a validation check in here. So if it's lowercase, then we basically need to go through each one. I mean, the path could also have a Boolean that says we already have a double in here, and we could avoid doing the extra stuff, right?
Since we already have a double. Oh, you're saying like
has double lowercase. Because it like basically we say if path dot has double lowercase. Oh, we would still need to know whether or not this character is in there.
If you check if it's in the frequency map, yeah. So if it's in the map, yeah, I think we're still kind of diving into the map. So
if n dot if n contains, or if path contains, if path dot freak, why am I not auto completing here?
That's weird.
Is
Is
it
it that you
complaining
took
just because I
away
didn't create
new?
it here? I'm not
Oh, I
convinced
guess
that
so,
we need
yeah.
this just yet, but
Mhm.
dot contains key
N.
if path dot has double lowercase, then we can continue right away, right?
Yeah.
Otherwise, path dot freak. I
Is there
mean,
like
it
a
doesn't,
object
we
dot
don't need a
values
frequency count
or
anymore.
yeah.
It's just the one double, right? So this really can just be a set. It doesn't need to have a counter on it, right? Because it's either one or this Boolean is set to true, right?
Because if we're going back and it's in the set and the Boolean's false,
Yeah,
we go forward.
right, exactly.
Yeah, that makes sense. Cool.
So this is just a hash set now of strings. Got to import it. This becomes a hash set.new. Let's make this a little bit easier to read, shall we? I'm surprised the formatter doesn't know how to handle that a little bit more gracefully, but so be it.
Yeah.
If path lowercase contains n, if it's already got a double lowercase, then we can't do it again. Otherwise, path dot has double lowercase equals true, right?
Because we're in that, yep. And then we push out
new path dot current equals n
current
dot clone.
Yep. Do we okay.
Not declared as mutable.
That was gonna be my question. How we're setting a value on path there. How does that work? Should we do a new path above that? Yeah.
This isn't super graceful code, but
I'm picking up what you're putting down. Yep.
Let's just call this double lowercase.
Wait, that resets it to false after you step over it. Doesn't it? Double lowercase equals new, but on line 49, double lowercase equals new path dot or path dot has dot. Yeah. There we go.
How's that?
That'll do it. Much better. I'm trying to run this no bugs. I don't want to break our streak. Oh.
Lowercase is actually, you know what? I think I like the other way that we're doing it better, just because
this feels very
path
understandable. Yeah.
dot lowercase dot insert n dot clone.
Is that so does lowercase come out mutable because new path is mutable?
Correct. Basically, when we clone this, it recursively clones all of these things. And so we fully own this new thing. And then it gets assigned to a mutable variable here. And so the memory that path points to recursively is mutually exclusive to the memory that new path recursively points to.
Yeah.
Because of the clone. And now we have full control.
I was just not sure if, yeah, I wasn't sure if lowercase needed to be separately annotated as mutable.
Oh,
but that's great.
Oh, so you're saying has this one or lower caves?
No, lowercase. But since it let you insert it, it clearly did. It is also allowed to be.
Oh, are you saying like would it have to be like mute this or something like that?
Yeah, I was like wondering. Yeah, I like that mutable is recursive too. I just didn't know that in Rust. I kind of want to run this. I think it's
It's looping pretty long. And it did something.
Okay. There was an order of magnitude.
Oh my god, this is correct. Holy shit.
Boom.
But you were saying. Sorry, you were saying.
Oh, that their example went from 200 to 3,000. So having ours go from 3,000 to 90,000 seems reasonable.
Yeah, I wonder if a release build is going to be that much faster. It's pretty fast.
Oh shit. Okay.
Whereas the debug build takes a while. The debug build has like a bunch of like bounds checking and all that kind of stuff that I think the release build knows to strip out. I won't pretend to know exactly what's going on under the hood. I feel like there's still some bounds checking at runtime that the release build will do, or else it would be unsound, right?
It's got to do something.
Yeah.
That's cool.
Okay.
That's I didn't realize that there was a fast version. Nice work.
Yeah, I bet that what's slowing us down is all these clones, right? I bet we could maybe turn these into references to strings, possibly, and that would be fine. We're never modifying any of the strings, so I wonder if. Let me commit this.
Yeah, do it.
And I don't want to keep you from your potatoes for too long.
Oh yeah, I should go eat dinner. They're probably perfectly cooked by now.
All right, I'm gonna let you go, and then I'm gonna continue. I'm gonna try to do this with string references and see if that speeds things up in the debug build at all.
Okay, sweet.